So welcome you back. So let us revisit what we were doing last time. So last time we started with location invariant estimation. So here the situation is as follows. So what I have is I have a data in terms of a random vector x1, x2, xn. This has a distribution function f, which belongs to a parametric family of distributions f theta. Theta belongs to capital theta, where f theta of x1, x2, xn is same as f of x1 minus theta 1, xn minus theta n. The vector x, which is x1, x2, xn, belongs to Rn. Theta is a parameter of interest, and I assume that my capital theta is whole of real line. Let me make, I've used two different f's over here. This f and this f may be different, so you can use this as g, doesn't matter. So here, the functional form of f is known. So what it suggests is that we are working in the parametric setup, where the distributions involved are all known except for the parameter theta. So this theta is, again, I assume that all thetas are same. So except for this parameter theta, which is a location parameter. And I gave you a definition of a location parameter last time. So to apply the invariance principle, what first I have to see is there a group of transformations under which this P, which is a family of distributions, is invariant. Then we saw that if we look at the addition group of transformation, collection of all those G says that C belongs to R, and where GC of x1, x2, xn is same as x1 plus C, xn plus C, with vector x belonging to my sample space chi, which I am taking as Rn over here. So then my P is invariant under G, and C is also varying over R. So then the first thing which we observed is P is invariant under G. That means if you apply any GC to the random vector x, you again get a distribution in P. And what is the induced group of transformations on parameter space and the Xn space? So let me call this as G bar. And the corresponding group of transformations on the Xn space is GC tilde. C belongs to R. What we see is if x1, x2, xn has a distribution function f of x1 minus theta, xn minus theta, then x1 plus c, x2 plus c, xn plus c will have a distribution same as this, except that theta gets changed to theta plus c. So that means my G bar C theta, which is the induced group of transformation on the parametric space, is nothing but theta plus c. Now everywhere my goal is to estimate theta. Now, of course, in the transform problem, theta gets replaced by theta plus c, so my xn's would also transform accordingly as per the invariance principle. So corresponding GC tilde A should be same as A plus C. A is an Xn space, which is whole R. Theta is in whole theta, which is again R. C is in R. C is in R. So P is invariant under a group of transformations G with corresponding induced group of transformations on the parametric space and Xn space given by this and this. So what I need now is just a loss function which is invariant. Then we saw that loss function L theta A, which is basically loss in estimating theta by A, is invariant if and only if L theta A is of the type W of A minus theta for some function W from R, and normally I take my loss function to be non-negative, so I can take my W to be non-negative. So that means its range is 0 to infinity. Now we had seen in our earlier lectures that a reasonable class of loss functions is one where L theta A is convex in A for every theta. So here L theta A would be convex in A for every theta if and only if W is convex in X, because if you take the double derivative of this respect to A for fixed theta, it would be nothing but W double prime A minus theta. So I need that to be non-negative, which is equivalent to saying that I need W double prime to be greater than or equal to 0, which is equivalent to saying that W is convex provided W is double differentiable. Otherwise also L theta A would be convex if and only if W is convex. So I assume is W is convex. W is a function of a real variable. L theta A is a function of two variables. So I needed L theta A to be convex for every theta as a function of A, which is equivalent to saying that W is convex. So with this, I can say that it is enough to consider only non-randomized. Non-randomized estimators. So let me denote Di to be the class of all non-randomized invariant estimators. Now, what we know is by definition delta belongs to Di if and only if delta of GCX, that means decision rule after applying the transformation of observation, is same as GC tilde delta x. Right? This is the definition of a invariance of a non-randomized estimator for every C belonging to R and X belonging to chi. Now, we know that this is equivalent to saying that delta of x is nothing but xn minus some function of, you can write down d1 of dn minus 1 for some function u1 from Rn minus 1 to R. Now, this I can replace by, because I know that xn is invariant, so I can replace this xn by any invariant estimator. That is what we saw over there. So let delta naught belonging to Di be fixed, then delta is in Di if and only if delta x is same as delta naught x minus u of d1 d2 dn minus 1 for some u. Now recall that what these d1 d2 dn minus 1s were. What were these d1 d2 dn minus 1? d1 was x1 minus xn, dn minus 1 was nothing but xn minus 1 minus xn. So in general, di is same as xi minus xn for I is equal to 1 to n minus 1. So now I know how does an invariant estimator looks like. An estimator delta would be invariant if it can be written as some invariant estimator minus some function of d1, d2, dn minus 1. Now, we also noted over here that g bar acts transitively on theta. So this also we did last time. G bar acts transitively What does that mean? That means any two elements of the parameter space theta are related through some g bar c. So that means that is for every theta 1, theta 2 belonging to theta, there exists a c belonging to R such that theta 1 is same as g bar c of theta 2. Right? That is very clear. Basically here theta 1 can be written as theta 2 plus theta 1 minus theta 2. So it is nothing but g bar of theta 1 minus theta 2, theta 2. Now we did a result before that if g bar acts transitively on P or the parameter space theta, then risk of any invariant estimator is constant. So this implies that for every delta belonging to di, R delta theta is constant. Constant in the sense that it does not depend on So that has made our life quite simple, because now I don't have to minimize risk function for every theta, because if it depended on theta, then for every estimator delta I am dealing with a risk function. Now minimizing a function for every theta is generally not possible unless you have some trivial cases. So it looks like in this case things may be simpler. So what I need to do is I need to look at any invariant rule which minimizes the risk for every theta among all theta. In situations where R delta theta is constant and I am trying to look at the best invariant estimator, such an estimator is called minimum risk invariant estimator. So let me give a definition. If an estimation problem under group of transformation D is such that the risk function of any invariant estimator is constant It is constant. What does that mean? Does not depend on theta. Then the invariant estimator which minimizes this risk is called the minimum risk estimator. Then the invariant estimator for which this constant risk is minimum is called the minimum risk invariant estimator. So let us try to find out the minimum risk invariant estimator. But before that, let us try to do a property of a convex function, which is well known. I am not going to prove it over here. You can look at any standard book on analysis having a chapter on convex functions to see the proof. So what it says is, let us say W is from R to R is convex, and non-monotone, because a convex function can also be monotone, like e to power x. So I am assuming that W from R to R is convex and non-monotone. Then W achieves its minimum. So that means W will have its minimum, and it is unique if W is strictly convex. Let me not spend time, although the proof is easier, but let me not spend much time on this over here. You can see any standard book on analysis to deal with it. So let us try to look at what is my class of. So let delta naught be a given invariant estimator. Then what is my class of all invariant estimator? This is nothing but delta u, such that u is a function of Rn minus 1 to R, where delta ux is nothing but delta naught x minus u of x. That is what we have seen. Any invariant, if you fix an invariant estimator delta naught, then any other invariant estimator can be written in terms of delta naught through this relation. So that means only variable over here is u of x, because delta naught I have fixed in the beginning. What I know is r delta theta, which is expected value when x has parameter theta of L theta Wx. That is what the risk of any invariant estimator is. But risk of any invariant estimator can be written, any invariant estimator can be written as delta naught x, where delta naught is fixed by us and u is varying. So if you vary delta, only this u varies. So this is same as E theta L. So W theta. So my loss function is L theta is nothing but W of A minus theta. So this is same as W of delta x minus theta. In fact, loss of any invariant estimator is constant. So this is same as R delta 1, because risk of any invariant estimator is constant. So R delta theta in fact is same as R delta 0. I can write now. That means risk at point 0, because risk no longer depends on theta. So this is same as what is the risk at 0? So that is same as expected value when x has a distribution corresponding to theta is equal to 0. L0, so everywhere I put theta as 0, which is same as expected value of theta is equal to 0. Then L0 delta x is nothing but W of A minus x. So in place of you have a Wx, Wx minus 0. But Wx I know can be written as W of any delta is delta naught x minus ux. only depends on d. D is nothing but d1 x1 minus xn, x2 minus xn, and xn minus x. So I write down this expectation as expectation of a conditional expectation. So this same as E theta 0. E theta is equal to 0 times W of delta naught x minus U of d given d. So expectation of a conditional expectation. So inner expectation is with respect to conditional distribution of x given d when theta is 0, and this is same as 0. So what I have to do? I have to find a u, a function u for which this is minimum. Now note that inside the inner expectation, d is fixed. This is conditional distribution of x given d when theta is equal to 0 is a true parameter. So what I try to is, since d is fixed, this ud may be treated as a constant. So suppose there exists a constant, suppose, so let me write down, for every fixed value of d, for every d belonging to, there exists a constant c star. Now this c star may depend on what d is, which minimizes this inner expectation. So let me call this as u star d. There exists a constant c, which is same as u star d, that minimizes psi c. You can put it c star, because psi c I am writing down as a function. C I am using for a variable. The c star is a fixed quantity. W of delta naught x minus c, because for a fixed d, this is a constant. So I'm trying to minimize this quantity for every fixed d, which is equivalent to saying that I minimize expect w naught x minus c for every fixed d into d. Then delta naught, so delta star x, which is delta naught x, minus u star d is the minimum risk invariant estimator. Right? So I try to minimize this inside expectation for every fixed t, which is done through minimization of this function. So very nice. Now this all was possible, things were simpler because I was able to minimize the inner expectation, because here I was minimizing risk only at one point, theta is equal to 0, because risk is constant. If risk was not constant, this would have been theta, and if you minimize this for every d, the minimizing thing may depend on theta. So as you vary theta, you may get different varying u star d's, so this will be depending on theta, and then this will no longer be an estimator. So here the fact that g bar acts transitively on parametric space theta made things simpler, because then I have to minimize this quantity only at theta is equal to 0. So minimizing thing will only depend on d, it will not depend on theta, and then consequently I'll get a proper estimator. Another thing is, this is unique under what conditions? Now note that if my w was non-monotone function, then if w is convex, expected value also of w would be, this would be a convex function of c. Why? Because you can take the double derivative, just to see an easy proof. Suppose w is twice differentiable. Take double derivative of this will be the, assuming that derivative you can take inside the expectation sign, it will be double derivative of w at the point w naught x minus c. So, double derivative with respect to c of psi is same as w double prime of delta naught x minus c and expectation. But w is convex, so that would be convex, greater than or equal to 0. So, psi c is a convex function of c. Not only that, if this was non-monotone, then its expectation value would also be non-monotone. So, this would be unique provided w is convex and non-monotone. So, now at least we know what is the minimum risk estimator. Let us try to see what is the minimum risk estimator in the very commonly used loss function, which is the squared error loss function. L theta a is suppose a minus theta whole square. This is called squared error So, the first thing I have to make sure is whether this loss function is invariant or not. For this to be invariant, it had to be a function of only of a minus theta. So, this is nothing but a minus theta whole square. So, it is only a function of a minus theta, so it is invariant. So, this is same as w of a minus theta, where what is my function wx is same as x square, provided w is strictly convex. Yeah. Convex is anyway given. Now, wx equal to x square, it is differentiable. So, to see it is convex, you have to just see the double derivative. The double derivative is positive, it is strictly convex. So, its double derivative is 2, so it is strictly convex. For every x. So, this means w is strictly convex. So, what is the minimizing thing over here? So, u star d minimizes expected value of theta is equal to 0 of w of delta naught x minus c whole square given d is equal to d. So, that means delta naught x minus c whole square given d is equal to d. Now, you know that mean square deviation from a point is minimum if this point c is nothing but the mean of this. So, that means u star d has to be same as E of theta is equal to 0 delta naught x given d is equal to d. And this would be the unique MRE. So, unique MRIE under square error loss function is delta star x, which is delta naught x. Now, this could be any invariant estimator of your choice minus u star d. And what is u star d? It is expect loop delta naught x minus given d is equal to d.